on the surface, when you look at the schedule of this course, you'll take a note that about 5 modules are somehow devoted to probability, including the exam that goes along with that. And then another 10 modules are associated with statistics. And it would seem, oh, okay, the course is 1/3 probability and 2/3 statistics. But the reality is that these two different worldviews, the probability world and the statistical world, actually overlap with each other in quite a significant way. And so some sort of breakdown between the two is not very easy to say. It might be more appropriate to say that 50% of the course is one and 50% of course is the other. And really the two worldviews that we'll get into here in a little bit are partially aided by thinking about the difference between a random variable and a random process. And so for our first example here, let's look at the design of a traffic signal. In the very literal sense of what you might think of when you hear a traffic signal. By the way, it's not traffic light, it is a traffic signal, signalized intersection. So let's have, yeah, no, you don't really care. But if we were going to be precise, and why wouldn't we want to be precise, we would refer to it as a signalized intersection. And in this very typical four-way intersection, we have vehicles arriving on the right-hand side of the road, and to prevent problems associated with collisions between vehicles and potentially between vehicles and pedestrians, we want to signalize in the typical way, our intersection with your typical 3-light, as in red, amber, and green. And yes, technically it's amber, not yellow. Alright, so some of the key aspects here for us here are thinking about what the random variable is in this intersection design, or design of the traffic signal. And so let's let X then be the number of vehicles that arrive from a particular direction. And typically the way we do this is in some sort of time interval, and that might be 30 seconds, it might be 45 seconds, it might be 60 seconds. There's a lot of different reasons why we might choose that different time interval, but the specific idea here is that a random variable is one that could have multiple outcomes. For any given delta t, we'll have a different number of vehicles that arrive at that approach to the intersection. And so, oh, well, okay, we have different approaches, so we'll let the x then, this random variable, we actually have 4 different random variables here. x1, x2, x3, x4. So that's not referring to the 4th value that we have, a 4th different delta t, but rather a different approach. And we could have just as easily used A and then B and C and D if that helps to communicate what you're doing. A lot of different ways, of course, to have done that. All right, now this is without regard, perhaps, to the sequence or what time during the day that we have the delta t, right? The statistics that we might have, the distribution that we might have is clearly going to be different for a signal that's during rush hour in an urban setting as opposed to one that's in the middle of the night. So that leads us to thinking about the random process, where now we might be thinking about what the properties are for this x for different time intervals during a 24-hour period. So maybe we collect over 30 seconds, chop up 24 hours into 30-second intervals and collect data across a single day. And we'll take just only one approach in that case, and let's draw this on a time axis. So there's our time in 24 hours. Halfway would be 12, and then at 1800, at 600, and of course at midnight. And we're measuring just one specific one, say X1. And of course, those specific data points, every 30 seconds, we're going to have a lot of them. Here in the early morning hours, not much, and then we start to have buildup of rush hour, and that'll fluctuate a little bit, get into mid-morning, drops down, midday, maybe, and bouncing around. Now we pick up for the evening rush hour, and maybe because this is directionally sensitive, outbound to downtown versus inbound to downtown, maybe we get a different kind of rate here, and depending on what city you are, maybe this actually looks pretty flat, but we get that down to near midnight and it drops off significantly. And so if we're interested in what these delta t's are during specific points in the day as a sequence, then that becomes a random process, as opposed to if we collect all, we don't differentiate when the delta t was collected during the day or during the week or during the year type of thing. Then if time doesn't matter when we collect the delta t, it's just a single random quantity, then that's just a random variable, as opposed to the random process where we do care about that as a function of time. So clearly in engineering you see examples of both of that, and the manufacturing context you might be thinking mostly about a random variable for a specific manufacturing process, as opposed to if you are doing something like this, design of a traffic signal, where clearly in that context the time of the day is going to matter quite a bit. Right? Now, let's say we always are looking at just 6 a.m. We decide we're going to design the traffic signal for the demand associated with 6 a.m. and we're only going to look at one specific delta t right there exactly at 6 a.m. And in that case, then we're no longer looking at a process, we're just simply looking at a random variable. Okay, one more example that might happen from your everyday life, you would never do this during work, and that is to play a game. You always do this on your free time, right? Or at lunchtime on your phone or what have you. And suppose you're very much into the game of Solitaire. You're like, oh yeah, come on, but wait a minute, let's do it Las Vegas style. Right, where in the Las Vegas style version of Solitaire, you are paying $1 per card to play. So that means $52 to play a single game. Right? And you end up earning or winning $5 per card that goes to the tableau, or in other words, that you score with. And so now your random variable, let's call it x, is going to be equal to your earnings for one game. And you can start asking questions such as, well, what's the probability that I have positive earnings in any one single play of the game? Right? Emphasizing just the single game, sort of like a coin flip almost. Right? Well, when we start looking at this as a process, then the sequence in a sense matters, and of course if you're playing with the fixed dollars, it certainly does matter. And so we'll let y then be equal to our cumulative earnings or winnings. In a game of chance, I suppose it would be winnings as opposed to earnings. Earnings suggesting that you actually are making some positive, direct, rational interventions to control, so to speak, what you get. And this will then, of course, just be the sum of the earnings from the individual game. So that y becomes some aspect of a process as opposed to just the individual outcomes of a single game. And here the one aspect that's key is, okay, this is kind of fun, think about in terms of your personal pursuits, but it's not very difficult at all to turn this directly back to engineering and engineering management and business decisions, where this is now associated with, say, the outcome associated with the cost of a certain product, and now we're talking about what's the cumulative cost of producing maybe a whole variety of different products. Right? That's more like a business kind of decision, and you can of course start to work this into different avenues of looking at profits. You can look at that. You can turn this entire thing into, well, what about investments in the stock market? What about my retirement income? Maybe this is the earnings in any one individual year for an investment, retirement investment, and what's going to happen in 30, 40, 50 years, or if you want to retire by the time you're 30, maybe it's only the sum over 10 years. And you start thinking about then the probability that you have the values that you want to be able to retire. Or again, you can easily start to spin this into this is something that we're measuring out of the manufacturing process, right? And that then we come over to the random process side of the world, and now we're looking at some cumulative effect of all of the little individual things. So this might be, say, the diameter at a single spot in a crankshaft, and then maybe diameter as along the length of the crankshaft becomes the random process, and the cumulative error that's associated with that. So maybe it's the error associated with the diameter in the crankshaft at one location versus some sort of sense of cumulative error along the length of the crankshaft, depending on what's of significance for that particular application, right? And so we're going to play with this notion of the difference between random variable and random process as we go along throughout the course, focusing predominantly on the random variable, but the notion of random processes is going to be a backdrop to what we do. And you might have noticed that my language here is sort of also steered towards asking probability questions. And that's going to be, probability as a whole is going to be exceptionally important to us as we get to the latter part of the course where we start analyzing data, because the analysis methods that we choose and the procedures and the conclusions that we develop from that are all going to come from the foundation of the probability view of the world. And so one way to characterize the difference is that probability tends to want to make predictions about the future, predictions about a population, as opposed to statistics tends to want to attempt to think about something in the past and summarizing data, summary statistics, and then how do we use those summary statistics then to make models for the probability side of the world. And so statistics has many different dimensions of it as well. It's not just about summarizing data or summarizing the past, but it's also about trying to make conclusions about populations as well. And is that population associated with a single random variable, or is that population really associated with a random process? Are all key critical kinds of pieces of information that we're interested in engineering management and engineering design.